Differentiation under the integral sign, D.U.I.S. I've done the very same integral on the board just a few minutes ago, but of course you don't want to be viewing that necessarily straight after this particular video. The integral that I've done on the board was e to the minus 2x sine of x over x. So a was basically equal to 2 and b was 1. And I was almost, when I wrote it on the board, I was almost going to do this one instead, but I changed my mind, so I left the original integral as it was, and now we're going to look at this most general form. Any conditions in there really? Yes, the a has to be definitely positive. Actually, let's make both of them positive. A has to be positive, so we have this decaying factor, reducing factor to make sure that the integral converges. Let's say for a and b being positive real numbers. Okay, so we're going to do it in this most general form. So we're going to define this integral I. I is a function of two parameters, I of a and b. Okay, of course, all of this will give you the x, of course, a dummy variable, so it will just disappear. This will be some expression in a's and b's. So this is what we got up there so far. So now we're going to do, of course, some kind of differentiation with respect to either a or b. So the question is which one? The answer is it doesn't really matter whether we treat a as a parameter and b as a proper constant or the other way around. I'm going to use it, I'm going to do the differentiation with respect to a for this particular example, but you can actually do it with respect to b. It will work exactly the same way, almost, okay? In fact, this particular integral, I have it in one of my books, which you can find on my website under differentiation. If you type madasmaths differentiation under the integral sign on the standard Google search engine, it'll come up with a book, and that is already in there, and I think there I've done it both ways. Okay, so let's go and start this differentiation. The idea is when we differentiate with respect to a, this exponential will produce a minus x coming to the front, which will cancel, of course, this x, and this now will become doable. So let's go. d(I) by dA. I'm using partial because now this is truly a function of two variables, is of course equal to d by dA of this particular integral. I don't know why I'm writing blue pen, I was meant to write in black, but it doesn't really matter now. Of this e to the minus ax. I haven't checked the quality of this pens on video, so I hope it's all okay. All right, dx. I'm going to write all the way across. So of course, by Leibniz rule, this is constant limits. It's a swapping integration and the integration there and the differentiation. So integral from naught to infinity d by dA of e to the minus ax sine bx over x. And we of course notice that this term here has no a dependence. So I'm gonna just do one more line. So I'm going to pull this outside the differential operator, sine of bx over x d by dA of e to the minus ax dx. And now finally, I'm going to do my differentiation, and my differentiation of that is going to be naught to infinity sine of bx over x. Differentiate that with respect to a is going to generate now a minus x to come to the front, and of course the exponential will remain unaltered. And this is now my last line. Of course, x's now will cancel. I mean, that was the whole point of doing all of this. And of course, we have that extra minus in there. Or what shall I do with this minus now? Shall I just reverse the limits, or shall I just put it on the outside? Probably I will reverse the limits because I feel like that at the moment. So this is equal to the minus there. I'm going to go now infinity to 0. And I'm going to have, of course, e to the minus ax sine bx dx. Not a very nice integral to do. Let's rub off and make some space for that. So all we need to record is the di by dA is this integral here. So because we're going to need it for reference later on, I have to be careful I don't rub off obviously things that we're going to need later. Let's see what the... I thought it was going to be easy actually writing on this tablet, but it's actually not as easy as I was expecting it. Okay, so di by dA is going to be the integral of infinity to 0 e to the minus ax sine of bx dx. Okay, when I done the video of course it wasn't in its general form. It had e to the minus 2x. I've done it by some bizarre way, this integral, but I was basically differentiating something which I felt it was the correct form, and then compared coefficients. Of course we can do double integration by parts. Of course we can use complex numbers, and I'm going to go complex numbers at this time. Okay, so, and I'm going to just carry it all the way through as well. So this is going to be now equal to this particular integral is the imaginary part, and then it's of course the integral of infinity to 0, and it's e to the minus ax, and this is going to be now e to the I.B.x. So when I take imaginary, this will give me of course the sine of bx. Of course the I is the part of what we say imaginary. This one doesn't get affected, so we're going to combine exponentials now. The imaginary part from infinity to 0, e to the is going to be now a minus a from this term here plus I.B lots of x dx, which of course now this is a constant, so we can just integrate that, still equal to the imaginary part. And now we begin putting evaluation brackets. So the evaluation brackets, I'm gonna now write 1 over, so now integrating the exponential, minus a plus I.B e to the minus a plus I.B lots of x to be integrated. I'm going to use these brackets also to mean the imaginary part as well as the evaluation limit, so double purpose ones. I'm not going to put another bracket on the outside. Okay, so we need to start tidying things up. So that's the imaginary part, and let's first of all conjugate this term. So it's going to be minus a minus IB over a squared plus b squared. So that's the conjugation of that. And I'm going to rewrite this back into how it was. So that is going to be e to the minus ax, that's this bit here, times e to the IBX. And now we can just do a variety of things, depends how you see it. Okay, we can actually put the limits. I don't want to go into sines and cosines. You can if you want, it's not a problem. But if you look at what happens in there, when you're putting x is equal to 0, or shall I just put sines and cosines? Let me just, because some people might not be confused about what I'm going to do. Let's say rather imaginary part, and I'm going to write there, of course, minus a minus IB over a squared plus b squared, and this is all real, e to the minus ax, and I'm going to put, of course, for this one, sine, not sine, sorry, I'm writing stupid things, I've gone absent-minded, so that is going to be, of course, cos of bx plus I sine bx, close that bracket, between infinity and 0. So I've got it in this particular form, and I'm going to evaluate and take a real real imaginary parts after that. So if you look what happens, I was going to do it there, but I thought let me just put sines and cosines. Okay, so when I put in there, still imaginary, okay, so when I put there 0, if you look at what's going to happen, the e to the 0 is of course 1. This is just a constant, it will always be there. This is 1, and of course 0 will kill this bit here completely, and it's going to make this into a a 0, so cos of 0, which is 1. So the thing that will survive is going to be minus a minus I.B over a squared plus b squared. That's on the top limit. What happens if we put infinity in there? Well, infinity, when we put it into the term e to the minus ax for a positive, it's irrelevant. This is finite. It will just die. This is just a constant. It's fixed. And therefore is minus 0, which I don't even need to write. So at the bottom limit, because of this factor, this produces nothing. And we want the imaginary part of this quantity. Let's lose that one, should be annoying. Let's close the bracket there. There's nothing else in there. And the imaginary part is, of course, the minus. That's the imaginary minus the b over a squared plus b squared. So this is the integration done. So let's leave it there, and I'm going to move it up there. So we just, the di by dA, which is this integral, we've done all the workings and it's equal to that. So let's lose all the unnecessary in-betweens. And I think we're nearly there. For this particular one, in its general form, I think complex numbers is definitely the way to go. So I did make, I think, the right choice, rather than using different methods to integrate that. So that's minus b over a squared plus b squared. Okay, so now this is not, of course, our integral. It's the differential of our integral. So now, in order to find what is the I of a comma b, we just need to integrate this with respect to a. We have to be careful here because b is a constant. So first of all, what is that equal to? Let's write it. First of all, it's going to be the integral minus b over a squared plus b squared, and this, of course, dA. So it looks a bit odd with a's and b's and dA. So this is going to be, this is a constant, of course, going to be there. This is the form that we are using in there. Okay, so the integral, I'm going to write it in with real numbers, how perhaps people are used to seeing this in further math. So let's not use a because that's bizarre. Okay, I'm going to use x squared plus b squared, which is the same as our constant here. Dx is, of course, 1 over b. That's the integral. That's an arctan. 1 over b arctan of x over b. So at the moment we can actually see that much better. So that's your x basically here, and that's your b as I wrote it in there. So that's minus b times 1 over b, as per here, arctan of x over b. So that's a over b plus c, of course. So the b's here will cancel. So this will now give us equal to minus, we've got a minus in there, the arctan of a over b plus c. Okay, how do we now proceed from there? Well, quite clear, we need to find this constant of integration. How are we going to find it? Well, we need to look at the original integral that we got up there, and let me just write it. I'll use a different color pen for this. I get to use my purple pen. I haven't used this for a long time. Okay, let's have a look how it shows on the video. So we have the integral from naught to infinity of e to the minus ax sine bx over x dx. That's my I of a or b up here. And we found that this is equal to a constant there minus the arctan of a over b. So for a suitable substitution for we can actually find this constant. What should the suitable substitution be for which letter? We can actually do it for a or b. Probably we'll be going for the a here because that's actually the parameter we used. So we can actually say if a is equal to 0, what happens in here? We're going to get the integral not to infinity. E to the 0 is 1, so it's going to be the sine of bx over x dx. And this is a little bit of a pain. Is c minus the arctan of 0. Okay. The arctan of 0 quite clearly is 0, so the c is just this constant, this integral. What is this integral? It turns out, I mean, this particular integral is independent of b there. The sine of bx over x is in fact equal to pi over 2. We can do a little substitution, lose this b, so you can make it as the sine of x over x. And of course, this will create a pi over 2, which is a standard result. But I don't want to do that. I don't want to be writing a lot of stuff. Maybe some people don't even know this fact at this stage. So what we can do instead, perhaps, okay, let's look again at our line up here. What can we substitute in there to work out a constant? Okay, look at this b here, for example. So if we say if b is equal to 0, okay, so that is equal to that. What happens if b is equal to 0? We have a problem because, of course, here this is positive, and this is going to go to positive infinity. So if b is equal to 0, we're going to get c minus the arctan. You have to forgive me for what I'm writing in there. The arctan of infinity, which is a little bit odd and bad, perhaps. And of course, if I put b is equal to 0, the sine of 0 is 0. So the whole integral, that's a 0 integrand. I don't care. It's just 0. So this, again, now will give us the constant much easier, because that's the constant minus pi over 2 is equal to pi over 2 here on the side. So the constant that we're looking for up there is pi over 2. That avoids perhaps using this particular integral, not to infinity, sine of x over x dx. And we don't even have it in this form. We had the b there, and we have to do another substitution and to kind of show, and this is just totally unnecessary. So we found the constant. The constant up here is in fact pi over 2. So I'm going to write pi over 2, and I'm going to rub off all these little workings. So let's see what we have achieved so far. I think we're done. It's just a case of writing the answer now in some kind of sensible way, so it's ready for use. So the integral, let's do it in red, this one. The integral, I've lost the limits in there as well. Sorry about that. That should be, of course, not actually, no, there was no limits there. My mistake. I'm sleeping, so ignore what I just said. Okay, so in this particular case, the integral from 0 to infinity, e to the minus ax sine of bx over x dx, from up here, turns out to be pi over 2 minus the arctan of a over b. We can leave it like that, but that's in fact the same as if we rewrite it, pi over 2 minus the arctan. Just think of it just with some numbers. Let's do it in degrees because it's probably easier to see. 90 degrees, take away the arctan of, let's say, 3/4, is the same as the arctan of 4/3. Or 90 take away the arctan over half is the same as arctan of 2. Very easy to verify, and just do the necessary trick to prove it. And therefore, I'm going to use this result to actually write this a little bit neater. So that's going to be, in fact, the arctan of b over a. And this is now the final answer for this particular integral. So I can't remember now. I think I had e to the minus 2x sine x over x on the one I've done on the board. And I think now I can do absolutely any integral for any a and any b which is positive. And I'm gonna sign out. And of course, this is the end. I hope you liked this video.